All right, welcome to The Explainer. Today we're going to dig into a paper that basically says we've been looking at AI all wrong. It's proposing this new idea called nested learning. And honestly, it might just be the key to building machines that can learn and remember forever.
So let's just jump right in with a question that's, well, it's simple, but it's also pretty profound. What if the most powerful AI systems, the ones we use every single day, had a really severe form of amnesia? What would that actually mean for their ability to grow and learn?
Well, here's the crazy part. They kind of do. The startling truth is after that huge initial training phase is done, large language models are, well, they're essentially static. They can't really learn from new conversations or new experiences and then bake that into their core knowledge. It's like they're frozen in time. And that right there brings us to this fundamental paradox with the AI we have today. On one hand, they're brilliant, but on the other, they're fundamentally forgetful.
So you can see on one side, yeah, LLMs can tap into this massive ocean of information they were trained on. That's why they seem so smart. But on the other side, they just can't create new, lasting memories. Anything new they come across, poof, it vanishes the second the conversation ends. And this limitation, it's shockingly similar to a specific neurological condition in humans.
The researchers behind this paper make this really powerful analogy. They compare it to anterograde amnesia. That's the condition where someone can't form new memories after, say, an injury. For an LLM, you can think of the injury as the moment its training stops. After that, its entire world is just two things: the very recent past, like the current conversation, and the distant past, its original training data. It's just stuck in a loop, always experiencing the present like it's the first time.
Okay, so if we want to build an AI that can actually break out of this loop, where do you even start? Where do you look for inspiration? Well, the authors of this paper turn to the absolute best learning machine we know of, the human brain.
Think about it. Our brains are absolute masters of continuous learning. They literally change their physical structure. That's neuroplasticity. When we're awake, they're in this rapid, online mode, quickly grabbing and stabilizing new, fragile memories. And then, when we're in an offline state, like when we're asleep, they get to work replaying, strengthening, and really weaving those memories into our long-term knowledge base.
And this image, it just illustrates the core idea so brilliantly. Our brain coordinates all this activity using different brain waves, right? You've got these slow delta waves when you're in a deep sleep, and then these super fast gamma waves when you're intensely focused. And that is the key. Different parts of the brain are operating on totally different timescales. So the big question becomes, what if we could build an AI that does the exact same thing?
And that biological inspiration is what leads us straight to this new paradigm, nested learning. It's a completely different way of thinking about the architecture of AI.
So the paper makes a pretty bold claim. It argues that our current view of deep learning, this picture we have of a simple, flat stack of layers, is just an illusion. It's a simplification that actually hides what's really going on under the hood.
Nested learning is all about pulling back that curtain. The idea is that a model isn't flat at all. It's actually a hierarchy of different learning systems, all nested inside each other. And each of these levels has its own job, its own context, and, this is the critical part, its own learning speed, its own update frequency.
Okay, and what's so cool about this slide is how it visualizes that whole idea. Look at the top. That's our traditional deep learning view. It's kind of like looking at a flattened, 2D picture of a 3D object. You're missing all the depth. But then look below. The nested learning view reveals that hidden depth. It shows you all the different levels and how the information is actually flowing between them. It just makes so much more sense.
So here's the thing. This isn't just some abstract academic theory. This new way of looking at things actually lets us see a hidden layer of complexity in the AI tools we're already using every single day.
So that begs the question, right? Can we take this nested lens and apply it to something super fundamental, like a standard optimizer? The very algorithm that actually trains the model in the first place?
And it turns out, yep, you absolutely can. The paper shows that even a common, everyday tool like gradient descent with momentum isn't just one single process. It's actually a two-level, nested learning system hiding in plain sight.
Here's how it breaks down. You've got this slow outer loop. That's what's updating the model's main parameters. You can think of that as its core long-term knowledge. But then you've also got this fast inner loop. And that's the momentum part. It acts kind of like a short-term memory, rapidly updating to capture the immediate trends it's seeing in the data. So you have a fast system and a slow system, working together, just like the brain, to learn more effectively.
Okay, so if even a simple optimizer has this hidden nested structure, what happens if you design a whole AI architecture with that idea in mind, right from the very beginning? Well, that's exactly what the authors did. They created a new architecture they call HOPE.
And you can see the difference right away. On the right, that's a standard transformer. It has one main feed-forward network, the FFN, and that kind of acts as its long-term memory. But then look at the left. That's HOPE. It has multiple FFNs, and each one is updating at a different speed, a different frequency. You've got a high-frequency one for immediate info, and then these slower ones for integrating knowledge over the long haul. HOPE is built from the ground up to learn more like a brain. It uses what the authors call a continuum memory system. Here's a good way to think about it. Imagine you're reading a book. The fast layers in your brain are just processing the words on the page, but at the same time, the slower layers are gradually piecing together the plot, the characters, the themes, integrating it all into your long-term memory. That is exactly what HOPE is designed to do, allowing it to constantly consolidate knowledge and literally modify itself over time.
All right, so we've got this really elegant theory, this new architecture inspired by the brain. It all sounds great, but does it actually work? I mean, does building an AI based on these nested principles actually lead to better performance?
It's a super compelling idea, no doubt about it. But in the world of AI, the ultimate proof is always in the numbers. It's all about the performance benchmarks. And well, the results really do speak for themselves. When they tested it on a whole bunch of common-sense reasoning tasks, the 1.3 billion parameter HOP model hit an average accuracy of over 57%. That is a huge improvement over a really strong baseline, the Transformer++. And that's not a small jump either. We're talking about a 9.5% relative improvement. That's a really significant leap, and it shows that this new nested way of thinking about learning isn't just theoretical. It has real, practical power. And all this leaves us with one final, pretty mind-blowing thought. We've been talking about a new architecture, sure, but the implications here are just so much bigger. If we can actually build an AI that never stops learning, one that can form new memories and adapt from every single interaction, just stop and think for a second. What would that make possible? It could fundamentally change everything we think we know about intelligence, both artificial and our own.